Today we're going to talk about Cauchy's integral formula and how it can be used to solve integrals. This theorem states that if a function is analytic in some simply connected domain D, and gamma is a simple closed contour with positive orientation in this domain D, then for any point C0 inside of gamma, we have that the function at this point can be determined by the following integral. The main consequence of this theorem is that if you know all the values for a function on gamma, then you can determine the integral, and hence all the values inside of gamma, by using this equation. So by merely knowing how a function behaves on gamma, then you know how it behaves for all the points inside of gamma. So in other words, analytic function's behavior in some domain is simply determined by its behavior on the boundary of this domain. I will not prove this theorem in this video, since I will make another one just for that. And when I made it, you can find the link to it in the description. Some good things to know about this theorem is that the formula, but rewritten, can be used to determine integrals, which is mostly what we are going to use it for in this course. The next thing to note is that if a point C0 would be outside instead of inside of gamma, then this expression here would be analytic on and inside of gamma, since we have removed the point C0, which is the only singularity for this expression. So the integral of this expression along gamma would be equal to 0 by Cauchy's integral theorem. So the main difference between these two theorems, Cauchy's integral theorem and Cauchy's integral formula, is that we are going to have to use Cauchy's integral formula when we're dealing with a singularity. By taking the derivatives of this formula, we get the following, which is called the generalized version of Cauchy's integral formula, which we can use to determine the value of a function's derivatives for points inside of gamma. And note here that if you let n be equal to 0, we get back the standard version of Cauchy's integral formula. The last thing I would like to touch on before we continue by doing some examples is that some books might state this theorem in a different way. They might state it something like this. And this is completely fine, since if a function is analytic in some domain D, and gamma is inside of this domain, then of course our function must be analytic on and inside of gamma, since gamma also lies inside of a domain. So let us continue by doing some examples. Here I would like us to compute all the integrals. And notice here that the contour gamma will be the same for each one of them. Gamma 1 will look something like this. And this contour would be really hard to parameterize if we had to solve these integrals the normal way. So it's kind of nice that we don't have to do that, since we are going to use Cauchy's integral formula to solve them instead. When solving these kinds of problems, you always want to start by marking the singularities of integrand, which in this case is going to be at c is equal to 1, since at this point we get a 0 in the denominator. So by doing this, we have managed to determine that the singularity is inside of gamma 1. So the whole thing is at least not equal to 0 by Cauchy's integral theorem. But we can continue by rewriting this expression just a bit, to make it more easy to see how we can apply the formula on this expression. So since the expression in the numerator, cosine, is analytic everywhere in the complex plane, we can now use Cauchy's integral formula to solve this integral. So now we can see that we can use the formula with the fact that the function f is going to be equal to cosine, which is fine, since cosine is going to be analytic everywhere in the complex plane. And then we can use that C0 is going to be our point of singularity, which is 1 in our case. And then we can see that n is going to have to be equal to 0, since in our expression we have c minus 1 raised to the power of 1, and this should be equal to c minus c0 raised to the power of n plus 1. So n plus 1 needs to be equal to 1, which is only the case if n is equal to 0. So by using this, we get the following. And note here that the 0 derivative of a function f is simply the function f. So that one becomes the following. And since we know that the function f is cosine, and 0 factorial is equal to 1, we get the following. And this thing is going to be our final answer. In our next example, we start once again by marking out our singularities, which is kind of hard to do the way the expression is written right now. But if I rewrite it for you by factoring out 3 in the denominator, we get the following. And since this thing is a factor, I'm just going to move it outside of the integral. And now you might more easily see that the singularity can be found at c is equal to 1/3. And since this point is inside of gamma, we have to continue by using Cauchy's integral formula to solve this integral. So by letting the function f be equal to cosine, since this thing once again will be analytic on the whole complex plane, and then c0 is going to be equal to our singularity, 1 divided by 3. And then we once again have that n is going to be equal to 0, we get the following. And by simplifying this a bit, we get our final answer. In our next example, we are going to have two factors in our denominator, and therefore we are going to have two singularities, one at c is equal to 1 and one at c is equal to 2. But notice here that the second singularity, c is equal to 2, is not contained inside the gamma, and therefore I can rewrite our expression to the following. And notice here that cosine divided by c minus 2 is always going to be analytic on and inside of gamma, since this expression's singularity, c is equal to 2, is not contained inside or on gamma. So now we can once again use Cauchy's integral formula, but this time our function f is going to be equal to cosine divided by c minus 2, since this thing will be analytic on and inside of gamma. And then we once again have c0 as our point of singularity, 1, and n is equal to 0, which will give us the following. And this thing can be simplified to the following. And now we can just move up our minus 1 and get our final answer. So since I think you and me are having such a great time doing all these kinds of math problems, let's do 3 more. The main difference in our next example compared to our earlier ones is that the factor in our denominator is raised to the power 2. But we start the same way as before and mark the singularities on the graph. And as you can see here, we're going to find that we have a singularity at c is equal to 1. And now we can use our formula once more with the fact that the function f is going to be equal to 2c raised to the power 2 plus 1, since this thing will always be analytic. c0 is going to be equal to our singularity, and n is going to be equal to 1 in this case, since the factor in the denominator was raised to the power of 2. And by using this, we get the following. And to continue from here, we have to determine the function's f's first derivative. And since we know what the function f looks like, we can quite easily determine that the derivative of this function is going to be equal to 4 times c. So by inserting this into the expression, we get the following. So the integral is going to be equal to 8 pi times I. In our last two examples, we are going to switch it up and use new contours for our integrations. So in example 5, we can see that we have a singularity at c is equal to 0 and one at c is equal to 1. But we can also notice that the contour is not simple, since it crosses itself. So we can therefore not use Cauchy's integral formula right from the start, since it only works for simple contours. But we can fix that by splitting up our big contour gamma into two smaller ones. Let's call them gamma 1 and gamma 2. And here I would like to notice that both of these two new contours are simple, and the fact that if you add these two paths together, you get the contour gamma. So since our path gamma is made up of the two separate paths gamma 1 and gamma 2, we can rewrite this expression up here to the following. So now we can try to solve these two integrals one at a time instead. Notice here that gamma 1 is positively orientated, while gamma 2 is negatively orientated, which means that we cannot use Cauchy's integral formula for a second integral, since that contour is orientated the wrong way. But we can fix that quite easily by knowing that the integral along some path gamma 2 is going to be equal to minus the integral along gamma 2 but taking in the other direction, which I'm going to denote here by minus gamma 2. And by using this, we can rewrite the expression up here to the following. And now we can use the formula 2 times, one for each integral. But first I want you to notice that each of these two integrals only contains one singularity. Gamma 2 only contains the singularity at 0, while gamma 1 only contains the singularity at 1. So this means that we can once again rewrite the expressions so that the only thing that is left in the denominator is the factor that corresponds to the singularity. Now we can once again use the formula for these two integrals. For the first one, we get that the function is going to be equal to 2c plus 1 divided by c, since this thing will be analytic everywhere on and inside of gamma 1. And then we're going to have that c0 is a singularity, so that's 1. And then we have that n is going to be equal to 1 in this case, since the factor in the denominator is raised to the power of 2. But before we continue, I'm just going to rewrite the function up here to something a little bit more simple. And for our next one, we are going to let the function f be equal to everything in the numerator, since this thing will be analytic inside and on minus gamma 2. And the singularity was at 0, so c0 is going to be equal to 0, and then in this case n is going to be equal to 0. When we use the formula for our first integral, we get the following. And here I would like you to note that the derivative of our function f is going to be equal to minus 1 divided by c raised to the power 2, which means that if we insert 1 into this derivative, we get the following. So with the first one done, we can continue to the second one. So we take minus the second integral, which is going to be equal to the following according to the formula. And here we have that the function f, which is a different function from the first one, evaluated at 0, is going to be equal to the following. So by simplifying this a bit, we get minus 2 pi I minus 2 pi I, which is simply equal to minus 4 pi I. In our last example, we start by marking the singularities, which can be found at c is equal to 2, and then you can notice here that our contour gamma is not simple. So we once more need to break this big one up into two smaller ones. And I can do that by creating these two contours, gamma 1 and gamma 2, which both are simple contours. And here once again you can note that our big contour gamma is going to be made up of the sum of gamma 1 and gamma 2. So this means that we can once again rewrite our expression up here to the following and determine the integrals one at a time. And when we now look at the orientation of gamma 1 and gamma 2, we can notice that both of them are positively orientated, which is great because now we can use the formula right from the start. And since both of these two contours encloses the same singularity, we are going to have to use the formula the same way both times. So by letting the function f be equal to c, and the singularity is at 2, so c0 is going to be equal to 2, and then we have that n is going to be equal to 0, we get the following for our first integral. And here I would like you to notice that f of 2 is simply going to be equal to 2, so we'll get the following. And now we can add the second integral, which is simply going to be the same. And by simplifying this a bit, we get 4 pi I plus 4 pi I, which is going to be equal to the following. And that was everything for this time. I hope you learned something about Cauchy's integral formula. And if you still have some questions, just let me know in the comments. And consider subscribing if you like what I do here. Thanks for watching.